All right, we are going to talk about how to deal with discontinuous functions in the Laplace transforms. So we start with the prototypical discontinuous function. It's known as the Heaviside function. Its graph looks like this. Here's the y-axis, the x-axis, here's some value a. The function is 0 until a, and then it immediately jumps to be equal to 1 after time a. While this may seem like something unrealistic, think about how it happens when you turn on a light switch, right? Something happens, nothing was happening before. So there's the Heaviside function. This is like turning on a switch. Okay, so we are going to talk about how we solve differential equations when we have a function like this involved. So to start with, we're going to first find the Laplace transform of this function. And we'll go to the definition of the Laplace transform. It's the integral from 0 to infinity of the function of t times e to the minus st dt. All right. Now, when t is between 0 and a, this function, the Heaviside function, is nothing. So really, this is only the integral from a to infinity, and from a to infinity, the Heaviside function is equal to 1. So we're really integrating 1 from a to infinity times e to the minus st dt. So this we know how to do from calculus. This is going to have to be the limit as, let's say, b goes to infinity of e to the minus st over s, because the variable here is t, evaluated at b minus the value evaluated at a. And when we let b go to infinity, we calculate the limit, we get e to the minus as over s. So there's our Laplace transform of the Heaviside function. Okay. So if we turn on at time 1, it's e to the minus s over s. If we turn on at time 2, it's e to the minus 2s over s, and so on and so forth. Okay, next we're going to do is we're going to try to solve for a differential equation when some of the data is a Heaviside function. Here's our function, or our differential equation. dy over dt plus y is equal to the Heaviside function, but turned on at time 3. So that's u3 of t. And let's take the initial value of 2. So we start at time 2, and then we see how the situation progresses. Now remember, until that function time turns on, for the first 3 seconds rather, this is dy over dt equals minus y. So we should have exponential growth for a while, but then we get something, or sorry, exponential decay for a little while, but then u adds a little bit of kick to dy over dt, and we should get some growth after that. So let's see what happens when we start moving with the Laplace transforms. So we take the Laplace transform of all the terms, Laplace transform of dy over dt, Laplace transform of y, which is, of course, is what we're going to have to solve for as time goes on, equals the Laplace transform of the Heaviside function turned on at time 3. All right. By the differential rule for Laplace's transform, we have s times the Laplace transform of y minus y at 0, which we know is 2. I'll replace it with that next time I write it. And then we add the Laplace transform of y. And now we've calculated what this is equal to. It is e to the minus 3s over s due to our calculation on the previous screen. So doing some substitution here, or moving things around, we have s plus 1 times the Laplace transform of y is equal to 2 plus e to the minus 3s over s. Great, we continue and isolate the Laplace transform of y. We get 2 over s plus 1 plus e to the minus 3s over s times the quantity s plus 1. Okay, now we're ready to take the inverse Laplace transform, and this part is not a problem, right? This part is going to go to 2e to the minus t. And that part corresponds to the initial value, and the dy over dt equals minus y, right? That would be exponential decay. This part doesn't involve the Heaviside function at all. This part does, though, and we don't have any values in our table that's going to help us deal with this, right? We're kind of stuck taking the inverse Laplace transform here. So let's pause this example and talk about how we're going to deal with this. So we're going to come back to this example eventually. Okay, we're going to talk about shifting and the Laplace transform. Let's say I have some function f. Looks like this. And I'm going to shift it forward in time, a units. So here's a units, and now the function's going to look like this, right? I had some original function, f, and now I want to delay f from happening until time a starts. And the question is, how do we do this? What does this arrow look like? Well, I argue that this would be called a function g, and g we could write as the Heaviside function turned on at time a times the function f shifted by a. Right? Perhaps you want to pause and think that through, but that's not too difficult, just some elementary shifting of a function. So now what we're going to do is we're going to find out what is the Laplace transform of g. What is the Laplace transform of this new shifted guy? And basically what I want is I want it in terms of the Laplace transform of f. Right? If I know the Laplace transform of f, and then I shift it by a units in time, what is the Laplace transform of that new function going to be? That's what we're trying to figure out. So our answer is going to be in terms of the Laplace transform of f. Right? Definition of Laplace transform, the integral from 0 to infinity of the function. So I'm copying down what g is here. Now, we have a Heaviside function here, so really we could ignore it and instead start our integration at a. Okay, this doesn't look quite right because we have this thing going on in the t minus a. So let's do a change in variables. Let's let u be t minus a. Then du is equal to dt. Now, t started at a, so u is going to start at 0. T ended at infinity. U is going to end at infinity as well. And now this is f of u times e to the minus s. Instead of t, t is now, of course, u plus a. But now we can pull out the e to the minus sa. When we do that, what remains? We have a function f times e to the minus su, integrated from 0 to infinity. That is just the Laplace transform of s in hiding, or of f in hiding. Right? So, when we time shift a function, the Laplace transform changes by being multiplied by e to the minus s times that time shift, a. So let's go back to the problem that we had from before. Well, let's Yeah, so this is what we want to record, right? The difference between the Laplace transform of a time-shifted function and the original function is this e to the minus sa, where a is the amount of units in time rightward we shifted the function. So let's go back to our problem. Okay, we were at this point in our calculation. We had that the Laplace transform of y was equal to 2 over s plus 1 plus e to the negative 3s over s times s plus 1. Okay, so now we recognize, oh, this e to the minus 3s, this is a time shift. So I'm going to pull it out and just leave what remains. So now what I'm going to do is I'm going to work on this. I'm going to do a partial fraction decomposition. And then I'll be able to recognize what I have the Laplace transform of. So now I have 2 over s plus 1 plus e to the minus 3s. This is a 1 over s minus 1 over s plus 1 if we do the partial fraction decomposition. So altogether then, distributing that through, this is e to the minus s times e to the minus 3s times 1 over s plus e to the minus 3s times 1 over s plus 1. So this is what the Laplace transform of y is. And now everything is such that we know the inverse Laplace transform. We can go backwards. So y is going to be equal to, this first term gives us 2 times e to the minus t from looking at our original table. This, okay, well, 1 over s is the Laplace transform of the function 1. So this is just that function time shifted. So this is going to be u3 of t, right? This is exactly the Heaviside function, right? That's the time shift of the Heaviside function. Sorry, the Laplace transform of the Heaviside function, this original thing we had here. And then this last part, okay, this is the function, this is the Laplace transform of the function e to the minus t. But we're time shifting it. So it's the Heaviside function times e to the minus t, but we're time shifting by 3 units, so we're not going to turn that on. We're not going to start the e to the minus t until time 3. So this part is the normal behavior. This is what happens for the first 2 seconds, or first 3 seconds. We have exponential decay. But then, as the time continues, we get these things added because we turned on the Heaviside function at time 3. So it affects the solution only after time 3, as one might suspect. So what we have to do is we have to recognize these e to the minus 3s's and pull them out so that what remains are things that we know the Laplace transform of.